Okay, let's get started. So feel free to pick up your homework ones here. Um, they were, on average, really good. Most of you did very well, so I was happy about that. So just okay, I'm not sure. Okay, we'll work with the hand that we're dealt. So hopefully the display still works. So just a reminder that homework 2 is due Friday. So just make sure to hand that in. I just put out homework 3. If any of you have done homework 2 and are thinking, I have nothing to do now. I want some more math to do. So homework 3 is out and due next Friday. Obviously on Valentine's Day because everyone loves math, right? So, okay. So the basic idea of homework 3 is to flesh out some of the ideas that we talked about last time with the probabilistic method. So last time we were trying to compute the bound on the number of rows n as the number of columns gets extremely large. And we saw that it was some constant times log k. That's what we saw last time. But what I want you to do here is actually compute the constant itself. So we said that n is big O log k, where the constant can depend on v and t because we fixed v and t last time. And what I want you to do here is actually compute that constant. So not sure why the display is having issues. That's still readable, right? No. Okay, it's fine now, so let's keep going. Here, what I want you to be able to do is to compute some function of v and t, where n is at most some function f that depends on v and t times log k. And it's not that difficult once you take this hint into consideration. Just solve the equation for when it equals 1, and then it's a lot easier. So that's that one. For the second question, we haven't really talked about this, but we will a little bit today. Well, what if I wanted to incorporate the redundancy that we talked about last time, at least a little bit? So here what we want is not that everything is covered at least once, but everything covered at least lambda times. So we looked at this equation. We can talk about it more again today if we need to. And what this equation says is the expected number of interactions that are covered at most lambda minus 1 time. So it doesn't satisfy the requirement that we want. So the problem with this is that there is no elementary solution for solving for n directly. Whereas with the first one, it's just easy. All you just do is set it equal to 1 and then just solve for n by taking logs and things. Whereas here, you can't do that. There's no elementary function to do that. So what I want you to do for this one is to actually compute the value of n adaptively. So what you would do is, say for this problem, you would just say, I'm going to temporarily set n equal to 1, and then just see if this equation is less than 1. If it isn't, make n go up by 1. If it isn't, make it go up by 1 and keep going up by 1 repeatedly until it becomes less than 1. And then you report that value of n. So that works. So for various parameter situations, I want you to look at multiple choices of the redundancy parameter, lambda. So what you'll be producing are scatter plots. And what you'll find is that on each individual figure, you're going to have 5 plots, one for each choice of lambda. And what you'll hopefully see is a plot that looks like this. So that's for lambda equal to 1, let's say, and then you'll see one for lambda equal to 2, and then you'll see another one for 3, etc. So I want you to actually see what does the probabilistic method look like as we increase the number of columns. Okay, any questions on homework 3? Okay, so let's go back to where we were last time. So we were starting to talk about this higher index version of the probabilistic method. So just to recap, we're trying to make an array uniformly at random and just see what's the probability that it is a covering array. But we were doing it in a different way by saying, let's look at the expected number of interactions that are left uncovered. What is the average number? And if we guarantee that that number is strictly less than 1, then there must be some covering array with no uncovered interactions because it's strictly less than 1. So we were talking about the case of lambda equal to 1 where everything's covered at least once. Let's talk about the case where we have to have everything covered at least lambda times. Well, we looked at this equation where the k choose t v to the t is the number of interactions, as we derived before. And the sum here is the probability of being covered at most lambda minus 1 times. So we're looking at the number of interactions and the probability of each one being left uncovered. So the number of something times the probability of that something is the expected number of that thing. So if the expected number is less than 1, then there must be a covering array, just like before. So I mentioned last time, but I'm going to go through it again, that this sum is really hard to work with in that I want to get some bound of the form n less than or equal to something where the thing on the right side has nothing to do, has no n's over there. But the problem is that this sum is really hard to extract the n out because there's an n upstairs here for the binomial coefficient, and there's one right here for in the exponent here. If it was only in one of the two, then it might be possible, but it's in both, and it turns out to not be possible with elementary methods. So one technique that I looked at is, well, if we want to just get an upper bound on this, this quantity and show that the upper bound is less than 1, then surely this thing is less than 1 because we're trying to get an upper bound. So what I did was, well, let's just look at each of the 3 terms in the sum and just determine what is the maximum that each one of those individually could be. Well, so let's look at the binomial coefficient first, so this guy right here. Well, if I have n choose 0, that's 1. If I have n choose 1, that's n. If I have n choose 2, that's even bigger. N choose 3 is even bigger. But at some point, the binomial coefficients are going to go up, and then at some point, they're going to go back down. So what you'll see if you actually plotted the binomial coefficient values, so if we have lambda getting bigger on the x-axis, and then the vertical axis is n choose lambda minus 1, for example, then what you would see, so this is an actual plot, this is just what it would look like. What you'll see is that it goes up like this, and then at some point right here, it's going to go back down. So the requirement right here of lambda being less than half of n, roughly, is basically just saying that we're only concerned with this bit right here. So if I make lambda too big, then the problem is that I might not be getting the maximum possible binomial coefficient, and then I can't claim it's an upper bound. So that's why we do that there. And then, yeah, so if lambda is small enough, then the largest possible binomial coefficient is just choosing when this index I in the sum is as big as possible, which is lambda minus 1. For the second term, which is some fraction p to the power I, well, that is at its most when the exponent is as small as possible, right? If you have something less than 1 to the power whatever, that's at maximum if the exponent is as small as possible because it's a fraction. And so that's achieved when I is equal to 0. I starts at 0 as the smallest value. Well, anything to the 0 is what? Is 1. So that's why I put the 1 here. And then same idea with the second one over here, where we have 1 minus p to some power. Well, that is, of course, achieved the maximum when the exponent is also as small as possible, because 1 minus p is also a fraction between 0 and 1. So that means if we have n minus I in the exponent, the maximum is when the I parameter is as small as possible, because it's n minus lambda. So, no, that was my mistake. Because we're subtracting I, we want I to be as large as possible. That's what I meant to say. The exponent we want as small as possible, but I itself needs to be as big as possible. Yeah. So when I is at its maximum when it's lambda minus 1. That's the maximum it ever attains. So that's why I have n minus lambda plus 1, because if we have n minus I, this is equal to n minus lambda minus 1, but distributing the minus sign gives you n minus lambda plus 1. So that's what you get there. So that's an upper bound on the original sum. It's not equal to, so whatever bound I get out of this, all I can claim is that the true answer is big O of this. So it's at most this. It might be asymptotically smaller, but we don't know for sure because it's just an upper bound. So I'm not going to go through the details because it's kind of hairy and it's not really that interesting. So if you look up this function called the Lambert W function, it turns out that you can show this bound right here. And then you may think, where in the hell did you come up with that term? Where did you find that? I literally just took this equation, set it equal to 1, and put it into Wolfram alpha. And out popped Lambert W, and I was like, okay, well, I'll just use this function, and by analyzing that function, we can get an asymptotic bound, which is nice. So the point here is that the details aren't really that important there. The important thing is that look at the bound that we get. So the naive solution was to take an existing covering array and duplicate it lambda times vertically. And we showed that it was at most lambda log k times lambda times log k. But here, now we've moved the lambda to a much smaller term, log k. So log k is exponentially smaller than log k, which is pretty nice, and is an additive factor too. Okay, so any questions on that? I'm not going to spend much more time on this because I want to get to actual other methods that work in practice. Okay, so this is actually a project idea that I think might be interesting. Has anyone ever heard of a Chernoff bound? If you haven't, it's actually really, really cool. So the idea is, like, if we want to look at a distribution, so let's say we have a distribution here, and you can think of this distribution as the peak here is the expected number of uncovered interactions, but sometimes you can get more uncovered interactions, sometimes you can get fewer. So what you can do is, let's just say that I want to determine the probability that I'm within this strip right here, where the strip is really, really narrow. So the turnoff bounds give you the probability, or at least an upper bound on the probability, that you're outside of this interval. So the turnoff bound you can actually use here to upper bound this sum in a completely different way. So by upper bounding the sum, and this is what you get. I can send you the details if you want, but it's really not that important. You can get a different bound here. So here we get a log k plus square root lambda log k. So if we actually look at what we've done with these two sums, then these are the two bounds that we get. So I don't know if we can do better than this. There hasn't seemed to be any work about whether we can improve either one of these. So the point here is that if lambda, the redundancy, is very, very big, then which one is better of these two? If lambda is huge, which one would be better? The one that has lambda times log times something, or square root lambda times something? Which one's better? The square root one. So the thing that you should notice here is that now there's an interplay between not just many columns, but the redundancy also really matters. If you have a really small redundancy, then the first one is much better because you're multiplying by a much smaller thing. Whereas if the index, which is lambda here, is very, very big, the second one's better. So it just depends on which one you're working with. Any questions on probabilistic method? I promise, no more probabilistic method or asymptotics or anything after this. Okay. So I wanted to talk about constructions, about like, how do we actually directly make these? Is there like a simple algorithm that I just, or a formula where I just say, in this position I put this value, in this position I put this value? So I typed these up over last weekend, and there's actually quite a bit of math in here. So I actually will just put those up on Slack as just a reference if you want to actually use some of these things, especially orthogonal arrays. They're actually very, very important in this domain. So they're more for a project, more than going over these in lecture. Yeah, so there's some other things about like, if we just take the exhaustive array, like the one you made in homework 1, and I just partition each of the rows into different classes, I can get a smaller covering array off of each of those. So I'm not going to talk about those that much. Okay, yeah, that's not what I wanted. This is what I wanted. So, so we're actually going to start talking about construction algorithms or methods to actually make these covering arrays. So the first one we're going to talk about is exact methods. So the point of this is you just plug in the parameters, and after a probably long time, it'll tell you the exact answer on how small you can make the covering array. So in other words, if we input TKV into some magic black box right here, and then out pops a can of TKV. So the smallest number of rows for which a covering array exists. So the reason why we're talking about this first is that you may wonder, well, is there a way that we can actually figure out the minimum number of rows directly? And of course, there is a way, as we'll see. But what we'll find out is that these methods are extremely slow in practice. And most people don't even use these anymore. And then we'll start talking about methods that match the asymptotics that we have derived, the log k performance that we talked about. They match those, but aren't guaranteed to give you the minimum number of rows. So there is a trade-off between computation versus the quality of the solution that you get. But we might as well just talk about exact methods because they're actually used in some respects that I can talk about. In fact, I have a paper deadline on Friday, and I'm actually using some of these methods in my paper. Okay, so the simple idea is, well, I have no idea how to make this thing. Just try every possible array. Just try everything, no thought, nothing. Just try every array. And for each one, just check if it's a covering array. And if you go through every single possible array and none of them work, then you just say, no covering array exists. But if you do find one, then that tells you, of course, there is a covering array. So what you can try is just try n equals v to the t, which is the minimum possible number of rows for any covering array, no matter what. And then if this doesn't work, increase n, not like that, increase n by 1, and then try again. So try every array with v to the t rows. If none of them are covering array, then try one more row. And then do it again. So this will stop at some point because if I have, like the exhaustive covering array that you made in homework 1, well, if you have one interaction per row, that tells you that there is a covering array by just having an interaction for every row. But of course, it might be too big. So at some point, this method will stop. So at some point, it'll stop. But is this a good method? I don't think so. Because if you have v to the t rows, so if n equals v to the t, and we have k columns, then the number of possible arrays is v to the nk, which is v to the k times v to the t, where v to the t is upstairs, which is horribly inefficient. And that's just for a particular n. That's the minimum. But if I need to increase n, this gets far worse. So this is not a good idea. But yeah, only very small cases can be checked by a clever backtracking method. In fact, that backtracking method is one of the project ideas I put in the PDF, and it might be worth exploring that because not many, there hasn't been much work on that recently. But I have this little point right here, which may or may not be interesting. And there hasn't been any work on this, so that might be an interesting idea. So in 290, did you talk about equivalence classes? Okay, I'll talk about them. Okay, so let's just say that we were tasked with partitioning the integers into even and odd numbers. Okay, so like if we have the set of all natural, let's just do natural numbers to make it easy. So 0, 1, 2, 3, 4, etc. And we were tasked to partition this set into evens and odds. So, I mean, it sounds really, really simple. So what are those two sets? Can you name some elements of the even set? 0, 2. Yeah, 0, 2, 4, etc. So, like, let's just make a set which is E, which is 0, 2, 4, 6, etc. And then, of course, the odd set is everything else. So let me ask you a question. Are 0 and 2 the same number? No. But in this particular task, like, are 0 and 2 both even? Yeah. So with respect to the even condition, 0 and 2 are indistinguishable. They are the same. They represent the same thing because they have the same property, which is that they're even. But they themselves are not the same. So these two right here are called equivalence classes. If I can spell it, equivalence classes. So that means that everything within a particular class we say are equal. They're the same thing. Whereas two elements from different classes, those are different. They're not the same. So if I pick, say, 2 and 1, they're not the same integer, of course, but they're also not the same with respect to the even and odd condition. So within each class, each of the elements are the same. So how does that help us here with the covering array problem? So remember when we were talking about I can swap two columns and it gives me this basically the same array, right? It's just I flip the columns. So here, if I flip, or not flip, so what are the things that we can do? We can swap two columns, and we can swap two rows, and we will say that the covering arrays that are formed by these are equivalent. Because if I do some of these operations, swapping rows and columns, and get some other array, I can revert those changes back into the original array. So they are equivalent in that sense. So you may think, well, in this exhaustive idea of just try every possible array, what would happen is we would be testing a lot of covering arrays that are equivalent to other ones. So we would test two arrays, but they may be equivalent to each other, and thus we're doing too much work. Another thing that you can do is permute values within a column. So that's another operation that we talked about that is that is equivalent to the original, because I can just revert the changes that I made within that column and get a covering array from that. The original covering array from that. So you may want to try looking at, as a project idea, of what are the number of equivalence classes of covering arrays. And then what you can do for an exhaustive idea is just to test one representative from each equivalence class versus just check everything. So that could substantially speed things up. And I don't think there's been any work on determining what is the number of equivalence classes. So that might be interesting to do. Any questions on what the equivalence classes are and everything? Okay, we have plenty of time. Okay, do I have anything else to say here? Yeah, so one backtracking method idea that I have in the project idea PDF is what you can do is you have an array so far, maybe empty or not, and then what you can do is generate a row that hasn't appeared before, and then recursively call the procedure with the modified array. And then what you can do based off of that is you're not going to generate any redundant rows, and barring some details that are in the PDF, you can actually do a backtracking method that way. So you just basically, you keep generating rows until you get a covering array, back up one level, try another row, and then go down that route, come back up, down, back up, and then all you would do is just report the minimum number of rows that you ever found. And that would guarantee to find the minimum number of rows, which is nice. And it avoids checking a lot of things that you would have checked by exhaustive methods, because by that method, you're not generating a row that you haven't seen before. So that's another thing that could improve the speed of this by only looking at arrays that have distinct rows. So if you have an array with 2 rows that are the same, then there's no point in checking it. So you only want to check arrays with distinct rows. Okay, so let's actually move on to a different method, which is integer programming. So how many of you have ever heard of integer programming? Okay, cool. So this is actually it used to be a widely used method for solving various problems. So like the shortest path problem can be phrased as an integer program. So what do I mean by integer program? What you would have is you have a set of constraints. I guess you have a set of variables and a set of constraints on those variables. And our task then for this set of variables and constraints, see if constraints can be satisfied all at the same time with integer values for the variables. So it might be worth it to do an example. So let's look at a simple program where we have x1 as a variable plus 3x2 is at most 7. So just one constraint. So is it possible to give x1 an integer, x2 an integer value such that this is satisfied? Yeah. So what's an example? Yeah, 1 for both of them. Yeah, so that's definitely an answer, or 1 and 2, or yeah, there are other ones. So it definitely is possible. Is there a way that we can make this unsatisfiable? So let's try 4x1 plus x2 at most 5. Yeah, so that's possible. So if I have 1 and 1 for both, it still is satisfiable. So what you would have in this program is that you have a set of constraints, and you want to determine if you can put an integer, crucially an integer, to each of the variables to satisfy all the constraints. So how is it done in this setting? So we're going to make a bunch of variables right here, x, I, j, l. So this is a common technique that you see when you are working with array type structures that can have that has a certain number of things that could appear at each position in the array. So x, I, j, l, we want that to mean that it is 1 if the position in row I, column j is L, and 0 otherwise. That's how we're interpreting it to be. There's no way to actually enforce that in the program. That's just what our mental model is supposed to be. If this thing is 1, then the element in row I, column j is L. We see that we have n times k times v variables. Why is that? Because the I index goes over all of the rows, the n rows. And then for each one of those, we could have any one of the k columns. So it's n times k. And each position in the array can be one of all v possible values. So n times k times v. So that's the number of variables that we get. Okay. So every cell contains an entry. So it's this sum right here. There's also something that I guess we can leave it out because it appears later. This says that every cell contains an entry. Well, could it theoretically be that I have an x, I, j, L1 set to 1 and x, I, j, L2, where L1 and L2 is not the same? could it theoretically be possible, ignoring the program, that both of those variables are set to 1? If I ignore the constraints. Yeah, so there's nothing. If I just make a bunch of variables and no constraints between them, they all can be 1 or 0, it doesn't matter. So why is this sum saying that every cell contains an entry? Well, suppose that the sum is 0. So notice here that the sum ranges over all possible values for a given position. So I and j are fixed. We're looking at a particular row and a particular column. And we're summing over all of the possible values that can be assigned there. So what if the sum was 0? Well, that means if we want what is called a 0-1 solution, so instead of integer, every variable has to be a 0 or a 1. So if every variable is 0 or a 1, and the sum is 0, what do we know about all of the variables in that position? If every variable is a 0 or a 1, and the sum is 0, what do we know about all those elements in the sum? Yeah, they're all zeros. Which means that in our mental model, there's nothing in that cell, which can't be possible. So, but why don't I enforce the condition that it's at least 1? Because if it's at least 1, then there is something in that cell. Why is it equal to 1?
It's more than 1 because 2 things.
Right. So if there are if it's, say, 2, then that means that there are 2 different values that are assigned to that position, which is not possible in the covering array. So, or any array, I guess. So that's why we enforce equal to 1. Okay, so that's just saying that every cell contains exactly 1 entry. Now we need the important condition that every interaction is covered. So what in the world is this even saying? So we have a sum and then a product and at least 1, and then for all sets of columns and values. So what are we even talking about here? So what does the condition of an interaction mean? The interaction must appear in the array somewhere. So does it matter, if I have this interaction in the first row, does it matter that it's covered in the first row or the second row or the third row? Or does it just have to appear in any row? It can appear in any row. Can it appear in 5 rows if we want it, if it's in 5 rows? Is that possible? Sure, it can be possible. In fact, on homework 2, you're answering that question. So that's why we have the at least 1 condition here. It's covered in at least 1 row. If we said equal to 1, then it's not a covering array anymore. So that's why it's at least 1. The sum here is ranging over all the possible rows, all n rows. And the product here is saying that if we have an interaction, and let's just say we're looking at a particular row, and we want to determine if it's in this row, then it must be that the first entry is fixed to the right value, second entry is fixed to the right value, third entry fixed to the right value, etc. All t values are exactly the ones in the right order. So if we have a set of t columns here, well, the thing in the j1th column must have value L1. It has to appear in the right order. So that's why we have a product here, because if any one of the t elements steps out of line, then we want that product to be 0. So for that reason, we need to, because it's a 0-1 solution that we're after, we need, if one of them falls out of line, we want the product to be 0. So if one of them is 0, then the product is 0. Yeah.
Sorry, I just have a clarifying question.
Yeah.
For the every cell contains an entry, you're setting it to 1 because each entry can only have 1 value, and the interactions can appear multiple times, which is why it's greater than 1.
Yes,
But
exactly.
if the value moves out of the place that it was, which you were just talking about in the t columns,
Mm-hmm.
then we have to set it to 0.
Yeah. Yeah, we're setting the product to 0.
Okay.
Yeah. So notice that there's a sum on the outside. So if the first row fails and the second one succeeds, we're fine.
Okay.
Which is exactly the condition that we want anyway. So as long as it appears in some row, which means that the sum is at least 1, then we're fine. And so some covering arrays back in the early 90s and 2000s were found with integer programming methods. But the problem is that look at what happens here. So what is the number of constraints here? So let's see. Well, this thing right here is just one constraint. But how many sets of columns do we have? No, how many different sets of columns do we have? Well, we have k choose t of them. And how many values may or may not be repeating are there? Well, if each one has v possible values, how many do I have in total? Not v choose, because I can have them repeat. It's v to the t. So we have v to the t here. So we have k choose t times v to the t different constraints, along with a lot of variables too. So the main reason why this hasn't really caught on is that the size of the program gets very big. And there are methods for integer programming that do run in polynomial time, but they, in practice, aren't that efficient in terms of how long they really take in practice. But there are methods that do run quickly in practice. I can give you a reference if you want it. That do run fast in practice, but the worst case runtime is exponential. So this is probably the reason why this hasn't really caught on. It might be interesting to see whether or not solvers for integer programming have gotten much faster in recent years. And different solvers for different paradigms in this domain really have sped up quite a bit. It's just I don't know this space very well, so it might be an interesting project idea to look at this. Okay, any questions on just this simple integer program? Okay, how much time? So let's look at this one. So another problem with this is, look at this right here. So it's a product of t different variables. So one of the issues with integer programs in general is that they do work for any situation, but if you have a particular structure of the program itself, then it runs much faster. So that is something called an integer linear program. So the program we developed had some variable times another one, times another one, times another one. It's not linear anymore because it's a product of multiple variables. We can make it linear by having a variable for each interaction. So we can actually have a variable for the entries in the covering array, the ones we made before, but we can make a whole lot of other variables corresponding to the interactions and relate the two sets of variables together. I'm not going to go over the details of that because this is also terrible. So you can actually relate the two sets of variables together and get a linear program, and linear program for solvers run a lot faster, which is nice. The problem with this is that the number of variables drastically increased here. Whereas before we had n times k times v, which is significantly smaller than this. So again, the size of the program is huge comparatively. So the size of the program is huge, which is why this hasn't caught on. So I already mentioned this, so it might be worth looking into. Another thing that hasn't been tried at all, which would be really interesting to look at, is just apply these methods just in the straightforward way, but substitute the 1 here for lambda for higher index covering arrays, incorporating redundancy. That hasn't been done at all. So it is definitely worth looking into. Okay, any questions on integer programming? Okay, so I'm only going to start this because we don't have a lot of time. So how many of you know what a graph is? Okay, yeah, so all of you. How many of you have heard of the graph coloring problem, like the proper coloring problem? So some of you. So the basic idea here is we have a graph and we want to color the vertices in such a way such that any pair of vertices that are connected to each other have different colors. So if I, for example, wanted to color this vertex green, should I be allowed to do that? No, because I have 2 vertices that are connected to each other that have the same color. So this term where you want to have different colors on endpoints is called proper coloring the graph. So proper coloring, you'll see in the literature, means color the vertices so that so the endpoints of an edge have different colors. And a common question is, well, what is the minimum number of colors that are possible? So one strategy, which is not really smart, is let's just color every single vertex a different color. Then no matter what happens, you can't violate the condition of properly coloring the graph. And in fact, that's the best you can do in some cases. So if you have, say, this graph right here, so every vertex is connected to every other vertex. What is the minimum number of colors for this graph to properly color? 4. Because if I try 3, well, there's going to be a duplicate somewhere, but they're connected, so it can't be possible to color them. So this is often called the complete graph on n vertices, and in this particular case, it's K4. And if you're interested in what this pretty graph in the center is, that's called the Peterson graph, which has a whole bunch of interesting properties in graph theory, but they're not really relevant here. And of course, if you check this Peterson graph, it has 3 colors, red, green, and blue. And I invite you to think, is it possible to color the Peterson graph with 2 colors? So 3 is obviously fine because you can just check it, but are 2 possible? So I invite you to figure out, how would you even check such a thing? You can try all possible colorings, but that's obviously inefficient. There's a much faster way. So you may think, well, how in the world does graph coloring have anything to do with covering arrays at all? So this is actually a very recent technique, but it has proved very, very, very good for a number of reasons. So what we're going to do is, you can think of a graph as the vertices are variables in some sense, and the edges between them represent a constraint that's between them. So the constraint is they can't have the same color. So what we do here is, let's make an interaction a vertex. So we make a bunch of vertices, which are each one going to be an interaction. You have a question? Okay. Yeah, so each one is an interaction. And we'll go over this next time. But I'm going to put an edge between 2 interactions if they can't appear in the same row. So the minimum number of colors for this graph is the minimum number of rows, because they can't appear in the same row on a particular edge. So I'll see you on Friday.